Go ahead.
So, good afternoon. I am Shamuta, doing my PhD in DAISY and University of Potsdam. My supervisor is Professor Martin Pohl. So, I would like to talk about the particle acceleration in core collapse supernova remnant expanding inside the wind bubble. So just a brief overview of my talk. So at first I will introduce you with the wind bubble and diffusive shock acceleration. Then the numerical modeling, how did we numerically model the diffusive shock acceleration at the supernova remnant shock. And then some of my results and the conclusions. So at first the stellar wind bubble. So the massive stars losses a considerable amount of their mass during the different evolutionary stages it evolves through. The wind density depends on the mass loss rate and the wind velocity. So when the stellar wind interacts with the ambient ISM, it creates the double shock structure formation like the forward shock and the reverse shock. So we call this reverse shock as wind termination shock, and in between there is the contact discontinuity. So in this way there are the different regions in the stellar wind bubble. The inner region is filled with the free stellar wind, and then the shocked stellar wind region, and the third region is the shocked interstellar gas, and in the outer one is the like unshocked ambient interstellar medium. So that's how the stellar activity can modify the CSM. And when the massive star explodes as the supernova remnant, the supernova remnant shock evolves through this modified circumstellar medium. Therefore, we can expect the like the different particle acceleration and also the emission from the supernova remnant, which is different from the supernova remnant when it expands inside the uniform environment, like for the type 1a. Now we know that the diffusive shock acceleration process is the acceleration of cosmic rays in the shock environment, and it predicts the power law spectrum in momentum. So here the power law index depends on the R, which is the compression ratio, and the compression ratio again depends on the Mach number of the shock. So when for the core collapse supernova remnant, when the shock evolves through this modified circumstellar medium, the Mach number will change because the hydrodynamics would be very complicated there in the circumstellar medium, and the temperature is also very high sometimes. So therefore, because of the change in Mach number, directly from the effect of the hydro, we can get like the modified spectra, which is modified from the p to the power -2 spectra, the standard DSA prediction. So to solve this diffusive shock acceleration at the supernova remnant forward shock, we obviously need the cosmic ray transport equation. Need to solve this cosmic ray transport equation, and for this we need the total hydrodynamic evolution of the supernova remnant and the magnetic field, because like the magnetic field is directly related to the diffusion coefficient, which controls the transportation of the particles and the spatial distribution of the particles inside the supernova remnant, and hence the emission from the supernova remnant. And the magnetic turbulence gives the scattering center for the cosmic rays. Therefore, the magnetic field is very important in this case, and we have solved this component by using the RATPAC code, like radiation acceleration transport parallel code, and we also are calculating the hydrodynamics by using the Pluto code. And we did all this calculation in 1D spherical symmetry, and we have used the co-moving grid for cosmic ray transport equation and the transport equation for turbulence. So we have described this component by using the different equations. So for the hydrodynamic evolution of the supernova remnant, we have the hydrodynamic equations, and for the the evolution of the background magnetic field, through the entire lifetime of the supernova remnant, we have calculated the induction equation, and then we have this cosmic ray transport equation. So for the cosmic ray transport equation, it's the total time dependent process to calculate the cosmic ray density, and we have included the diffusion, advection, and cooling term. So here cooling includes the synchrotron cooling and also the inverse Compton cooling. And we have injected the particles from the thermal pool at the supernova remnant shock. And then last but not the least, the magnetic turbulence. So we have calculated the transport equation for the magnetic turbulence. And here we only consider the self-consistent growth of the resonant instability. So we only consider the alphanic mode. And then we have solved this equation for the entire lifetime of the supernova remnant. So we have solved these four equations parallelly by using our code. Now, so today I will show you the particle acceleration at the supernova remnant with progenitor star, 20 solar mass star, and 60 solar mass star. So this 20 solar mass star evolves to the red supergiant phase after the main sequence, and 60 solar mass star, which is a very massive star, so it evolves to luminous blue variable and Wolf-Rayet phase after the main sequence. So red supergiant wind is very dense wind, and luminous blue variable wind is also very dense wind, and the Wolf-Rayet wind is less denser wind. So for the 60 solar mass star, you can get the effect from the interaction between the less dense wind and the very dense wind in the wind bubble. And then for the diffusion coefficient, we have used the Bohm-like diffusion, when the diffusion length is comparable with the gyro radius of the particles, and it is like the time independent. So here we did not calculate any the time independently anything. But another is like alphanic diffusion. So here we have calculate this turbulence energy density by using the transport equation of magnetic turbulence. So now this is the hydrodynamics just after the supernova explosion for the 20 solar mass star and the 60 solar mass star. So for 20 solar mass star, you can see the dense red supergiant wind here and the less denser main sequence wind here. And then in the 60 solar mass star, you have the free wind, like 1 by r square free wind region, and here you can see a lot of discontinuities inside the shocked wind. So this arises because of the interaction between the dense LBV wind and less denser Wolf-Rayet wind. Another thing which I want to highlight is that for the 60 solar mass star, the shocked wind region is very hot here, so above 10 to the power 8 Kelvin. But for the 20 solar mass star, only the shocked main sequence wind is very hot. Now we did not calculate the magnetic field by doing the MHD simulation for the entire lifetime of the star, because it would be very complicated and computationally expensive. That's why we just parameterized it based on the theoretical knowledge. So for the 20 solar mass star and 60 solar mass star, for both of them, we have considered the toroidal magnetic field proportional to 1 by r in the free wind. And then according to the density jump, we have just parameterized the magnetic field. And then from the flux conservation, we have calculated the magnetic field and in the shocked ISM. And in the ISM, we have parameterized the magnetic field in such a way so that the forward shock of wind bubble should be super alphanic and as well as supersonic. So then, these are our results. So for the 20 solar mass star and 60 solar mass star wind bubble, when the supernova shock evolves to them, so this is the velocities for both of them, and these are the sharp shock compression ratio. So both of the cases you can see a lot of jumps in the supernova remnant forward shock velocity. So this arises because when the forward shock evolves through the modified circumstellar medium, it interacted with a lot of discontinuities which presented in the wind bubble. And so as the effect of the change in Mach number, the compression ratio changes. So for the 60 solar mass star, you can see that the shock evolves through a very hot bubble. So that's why the compression ratio diverges from the value 4, so which is the standard DAC prediction, and the compression ratio reaches to 1.5. So we can expect a very soft spectra for the 60 solar mass star. So now for the 60 solar mass star, this calculation has been done by for the Bohm-like diffusion. So here you can see even at the early stage, we have got a very softer spectra directed, which is a direct effect from the hydrodynamics. And here the spectral index reaches to almost close to 2.5. And for the alphanic diffusion, the spectra also depends on the growth and also the damping of the Alfvén wave, and also on the cascading, because here the system becomes very nonlinear. And since we got the softer spectra in the lower energy in this case, so these all are the volume averaged forward shock downstream spectra. Now, our simulation grid has been extended to 65 times of shock radius. So if we consider the total volume, like we have considered all the protons which are inside this 65 times shock radius, in this region, so then we got this total emission, like the total proton number spectra, and then this is the downstream spectra, and this is like the upstream spectra. So for the alphanic diffusion, so at the later times, because of the reduction in because of the reduction in the cosmic ray pressure gradient, the alphanic wave would be very weak driven. So that's why the diffusion coefficient becomes very large, and the high energy particles will be diffused upstream. They will not confined in the shock region. So that's why they are just escaping from the deep downstream to upstream. So that's why at the high energy we can get a very softer spectra by using the Alfvén diffusion. So directly from the hydrodynamics, we can create the softer spectra uh, at much earlier time and also in the low energy. But by using the Alfvén diffusion, we can get the softer spectra at very late stage and at the high energy, almost above 1 to 10 GeV. Now, if we just do the same calculation with a much lower mass solar mass star progenitor, so here you can see that the spectra is not softer, because we don't have the wind bubble is so hot to soften the spectra. But at the later times, because of the effect from the Alfvén diffusion, we can get the softer spectra. So here you can see the escape of the particles in the upstream, and we can get the softer spectra with the time evolution at the late stage. So the progenitor star really has a significant impact on the spectral modification. So with the hydrodynamic effect, we can get the softer spectra at early stage, but from the Alfvén diffusion, we can get the softer spectra at the very late stage of the evolution and in the high energy regime. So these all things, and also the circumstellar magnetic field has a significant impact on the emission from the supernova remnant and also the morphology. So these all are out of scope because I don't have much time to show all of them. So if you are interested, you can ask me, or maybe just go through these two papers, because here we have described that how the circumstellar magnetic field has an impact on the emission from the supernova remnant, and also like here we extensively describe that how the interaction between the circumstellar medium and the supernova remnant changes the emission from the supernova remnant and also the morphology. Thank you very much for